Hi, everyone. My name is BERT. I work as a senior developer advocate for AI and machine learning at AWS. In this session, I'm going to introduce you to BERT, and I'm also showing you how you can visualize the BERT attention for natural language understanding use cases using Amazon SageMaker. So a couple of words about me. Next to being a developer advocate, I'm also co-author of the upcoming O'Reilly book, Data Science on AWS, which I write together with my colleague, Chris Brackley. I'm also co-author and co-founder of the Düsseldorf chapter of Women in Big Data. Before joining AWS, I worked at companies such as Cisco and MapR. All right, so let's have a look at this session's agenda. First of all, I'm going to quickly introduce you to NLP, talk briefly about the history of the algorithms and concepts, and then we're really going to dive deeper into the BERT family of models, and I'm going to show you a little bit more under the covers how the BERT attention works, and obviously you might know the famous paper called Attention is All You Need. Then we'll see a demo of how you can visualize the BERT attention in model training using Amazon SageMaker. All right, so let's start with a brief introduction to NLP for those of you who might just start out in this field. So the problem statement in natural language processing is really to find a mathematical representation of the language. And NLP is really a major field in AI nowadays, and it has been studied for quite a while. And if you look at NLP applications, they require a language model in order to predict a next word. And those vocabulary sizes can be hundreds of thousands of words across millions of documents. So finding those mathematical representations of language is really not an easy task. And as I said, the research in the field of NLP goes back quite a while. So the English linguist Firth actually coined the phrase, "You shall know a word by the company it keeps," already back in 1957. And they started out pretty easy with word vectors. And word vectors are built from co-occurrence counts, and they're also called word embeddings. They can be high dimensional, at least 50 dimensions, up to 300 dimensions. And a nice thing about creating those word vectors is that you can also encode semantics and meaning. So for example, words with similar meaning should have similar vectors. For example, car should have a similar vector to automobile or sedan. And this is basically the magic behind how you can figure out that king minus man plus woman is queen. Because what you're doing is basically calculating distances between vectors. So for example, the distance between Paris and France should be similar to the distance between Berlin and Germany. Or the distance between hot and hotter should be similar to the distance between cold and colder. Isn't that cool? So the high-level steps in starting with building NLP and NLP models, you really start from a large text corpus. And that could be hundreds of millions of words, sometimes even billions. So many of the famous and popular models are trained, for example, on Wikipedia or corpus of book collections. Then you pre-process the corpus into tokens. So for example, hello world gets split up, as you can see here, into the different words. And then you build the vocabulary from those tokens. And you learn vector representations for the vocabulary. And if this sounds like a lot of work, it definitely is. But the good news is we can actually use pre-trained models that have already those existing vector representations. And we will see this when we start with BERT. So a couple of popular NLP use cases, and probably you heard of them already: representation learning, machine translation, text classification, language modeling, sentiment analysis, named entity recognition, or question answering. And we will also see some examples here in a bit. All right, that was a very brief introduction to NLP. And let's move on to the algorithms and concepts. if we look back to the evolution of NLP algorithms, we see that a lot of them really kind of emerged in the last couple of years. So in January 2013, Word2Vec got introduced. And Word2Vec is very popular still nowadays. It's a shallow neural network, and it's also known for the continuous bag of words and the continuous scriptgram concepts. Then in January 14, GloVe got introduced, and GloVe changed the concept by introducing matrix factorization. In July 16, fast text emerged, and this is an extension to Word2Vec, where each word is treated as a subset of words, character engrams. But Word2Vec and the family of those models have some limitations. For example, some words have different meanings, right? I could say, Kevin, stop throwing rocks, and also machine learning rocks. And as a human, you spot right away that rocks has a totally different meaning in those two sentences. But Word2Vec would encode the word into the same vector. So it's not really good in catching and capturing those different meanings. And this is partly also due to the bidirectional context that is missing. So those algorithms don't really take the whole context left to right and right to left into consideration at the same time. So this opened really the door for more research and for new models. In June 2017, transformers got introduced. And this is also where the famous paper, "Attention is all you need," comes from. And we will see how that works in the BERT section here. Afterwards, ELMO got created, and ELMO stands for Embeddings from Language Models. And I call it a pseudo bidirectional context because it's trying to address this bidirectional context problem, but it's using two unidirectional LSTMs for that purpose. So it's doing one path and another path. So not really true bidirectional. But thanks to BERT, which got introduced in October 18, we now have a concept and a model that is able to do this true bidirectional attention. BERT is replacing the LSTMs actually by this transformer architecture that got introduced the year before. All right, that was a brief walkthrough on the different models and a little bit what happened the last couple of years. Now let's really jump into the BERT family of models and see why they've become so popular. So BERT stands for Bidirectional Encoder Representation from Transformers. And BERT improves on ELMO in a couple of things. It replaces LSTMs with transformers, which deal better with those long-term dependencies. It's also, as I said, truly bidirectional, left to right and right to left, because it's learning it in the same network. And words are randomly masked during training, and sentences are randomly paired to improve next sentence predictions. And those are two concepts which BERT introduces in the training phase. And luckily for us, BERT is already available pre-trained, so we don't have to build it from scratch ourselves. We can use BERT base or BERT large, for example, and there's many, many more. So let's have a look at BERT pre-training and fine-tuning. And here you can see that the first part of building the BERT model is an unsupervised training. And here it's taking generic pre-training data coming from a large collection of text, books, corpus, and Wikipedia. And then it's running this masked language model where it's masking some of the tokens to predict the actual token, and also does this step of next sentence prediction in parallel. And when you're taking a pre-trained model, you can actually start for the next phase, which is fine-tuning that to your domain-specific data. And here it really depends on what you're training BERT on, whether it's question and answer, text classification, or named entity recognition, as just examples. And as I said, BERT really created this large collection of new models based on BERT that are domain-specific, like clinical BERT, focusing on healthcare, SciBERT, which is fine-tuned to scientific language, or specific language models like Common BERT for French, German BERT for German language, and a lot more. So let's have a quick look how BERT works under the covers before we start visualizing. So the first step is really creating those BERT embeddings. And here you can see the flow starting from bottom up. So at the bottom, you see the raw input, which is, for example, 2 sentences. Tom likes cats, Liz likes dogs. And the first step is then to tokenize, if you remember. And in this case, BERT uses a library called WordPiece to tokenize. And it's also introducing some separator tokens, CLS for classification, and the separator token to mark the separation between sentences here. Then with those tokens, we actually create token embeddings. And those are 768-dimensional vector representations for that specific word or token. So here we're passing in and we're seeing the input ID from that lookup table. We're also having an input mask, just in case we're passing in shorter sequences and the algorithm needs to pad. And then we also do a segment embedding, which is just showing whether it belongs to the input 1 or input 2. And also the position is important. So which token is on which position in this input sequence. All right, and then we do an element-wise sum of those embeddings, and we do have the final embedding for the BERT model. Looking at the different layers now and the different components. So once we have this input embedding, this is passed into a transformer block. And depending on which model you're using, BERT base has 12 of those, BERT large has 24 of those. And really the core concept here is this attention layer. So the transformer models with BERT as a prominent example are sequence models. And they really rely on that attention mechanism to capture the long-term dependencies. And also, they don't just have a single attention head, what it's called. They do have a couple of those, so it's a multi-head attention. And also, again, depending on which model you use, it can be 12 or 16 in this layer. So overall, BERT can leverage 384 attention mechanisms as those transformer blocks are stacked. And next to this attention, it also has a feed-forward layer, which is a fully connected layer, which contains most of the parameters, and residual connections and layer normalization. And then, after stacking those transformer blocks and running through, you would actually then adopt it to the actual downstream task, whether question answering, text classification, etc. So coming to the attention, and this is really the famous paper, which you probably all know, attention is all you need. And to put it simply, attention is really assigning weight to input features based on their importance to a given task. And here it's visualized. So if you want to understand how attention is calculated, it's simply a function that takes X as input, and you can see X here on the right side being 3 tokens, I like movies. And the attention returns another sequence Y of the same length, composed of vectors of the same length as those in X. And each vector in Y is a weighted average of the vectors in X. But as you can see here in front of X, we do have weights. And the weights actually show how much the model attends to each input in X when computing the weighted average. So how do we get to those attention weights, right? How do we figure that out? And to understand that, we have to understand that there's also another level of detail in this vector creation. So BERT has compatibility functions, which assigns the score to each pair of words, indicating how strongly they should attend to one another. And to do that, it creates 2 more vectors, a query vector and a key vector, which gets assigned to each word. And those are really linear transformations. And then the compatibility score is the dot product of the query vector of one word and the key vector of the other. So for example, if I want to see for the token movies, which other token it attends to, I would multiply that with a dot product to all of the key vectors, and you will see that score. So here in this example, I take movies and do the calculations with the 3 different keys. And the attention weight is then normalized compatibility score. So you're applying a softmax over those scores. And those are the weights you then use to calculate what we've seen before, the actual attention. All right, so now as we understand it a little bit better, how can we now understand why BERT is making certain predictions? And here's just an example of attention patterns. So when we visualize now in the next step, we will see that there's certain patterns that might come up regularly. So some of them are maybe that a lot of the attention focuses on the delimiters, on the separators. And this is really kind of when BERT doesn't find any other input token to pay attention to. Or the pattern looks like a bag of words, meaning it's attending fairly evenly across all of the words in the same sentence. And then you have next word attention patterns, and here the attention is focused on the next word in the input sequence. And there's a couple of more. So this is something you probably want to look out when visualizing. Okay, so putting all pieces together. So first of all, we started with converting the raw input text into BERT input embeddings. And one step in here is the word piece tokenization. Then the attention head takes the sequence of vectors corresponding to the tokens of the input sequence. And each input vector is transformed into this query, key, and its actual value through separate linear transformations. The attention head then computes the attention weights between all pairs of words as softmax normalized dot products between query and key vectors. And the output of the attention head is then the weighted sum of all of the value vectors. All right, that was a crash course in how BERT works. So let's come to the fun part and visualize. And part of this discussion is really, is attention explanation of the model? And I've linked here 2 papers because this is an area of active discussion. So one part of the research community says attention doesn't explain, right? It just shows you the patterns. And other parts in the research group are actually saying it's not an explanation, right? So it's really 2 fun papers if you have some time to read. So the root cause again, and the task is, how can we identify the causes of incorrect model predictions? And visualization is definitely one part, which helps us to understand the model maybe a little bit better. But to really explain, there might be a couple of more steps that are needed. So let's start with the visualization. And here's actually an open source tool that kind of created those terms and forms of visualizations. One is the attention head view, which is exactly what I quickly showed you already, like where you see the input tokens and where it attends to depending on the attention head you're in. Then there's a model view which shows all of the attention heads across all the layers, is the middle picture here. And then you can also have a neuron view which visualizes the individual neurons in the query and key vectors to show how they are used to compute the attention. So let's actually do this. And here's just one example if you're interested in how you can use that to detect certain things. So in this paper about the visualization of BERT, the authors use a sample like the Eminem tune was totally awesome. And the second sentence, dude, that song from Eminem was sick, and sick in the meaning of awesome. And you can see that the model actually doesn't attend high between awesome and sick. So it doesn't see those terms as being highly correlated, meaning positive. So there's a lot you can see in those visualizations. All right, so let's do a demo. And before I start the demo, I just want to quickly show you the tools I'm using. So I'm going to use Amazon SageMaker, which is a fully managed service from AWS that helps you to build, train, and tune your models. And as part of this service, there is a specific functionality called SageMaker Debugger, which helps us to get insights into the actual model training and to write out the tensors, because those tensor informations about gradient, loss, weights, etc., is what we need to also extract our attention weights, for example, and to visualize. So this is the tool I'm going to use. And Debugger really gives us that functionality. It captures data with zero code changes. It can do automatic error detection with a lot of built-in rules, for example, when gradients are vanishing, loss is not decreasing of your model. And we're specifically going to use the real-time monitoring to capture all the tensor information during training to see what's going on. And here's an example of those built-in rules. So you can basically create hooks into your model training and then see and plot, for example, gradients. So you can see the distribution, and if you have a vanishing gradient problem or exploding gradients, activations, losses, etc. So this is what we're going to try now to do with our BERT model. All right, let's jump into the demo part. All right, so here I'm in my Amazon SageMaker environment, and I do have a demo notebook here. So this is a regular Jupyter notebook. And I'm going to show you now how you can set up this debugger functionality to get the information. And in this notebook, I'm going to use Gluon NLP to fine-tune a pre-trained BERT model on the Stanford question and answering data set. And then we will also use the debugger to monitor what's going on during the model training. All right, so here you see a sample visualization across the first 20 input tokens for the first 10 iterations. And we're going to build it now ourselves. So the first part is here, I'm installing SageMaker Debugger. So I'm doing a pip install of the Python SDK. I'm setting up the other AWS Python SDKs that are needed to interact with my services. And then for the actual training, obviously, I do need a training script. So here I do have a training.py file, which contains the actual training code. And it downloads a BERT model from the Gluon NLP model suite. It fine-tunes the model on the Stanford question answering data set. And then we can actually also see how to include those debugger hooks. So again, here is the training script if you want to have a look. I also give you the link to all of the training code here in the resource section. And I'm basically then, as a next step, create my estimator. So here I'm creating the MXNet estimator object. I'm pointing it to this training script. And this one I'm actually running on a GPU-based instance on AWS. So here I'm pulling in a P3 to X large instance. I'm running it in a single instance. You can also do distributed training if you add here maybe a 2 or a 3. Passing in framework version, hyperparameters, etc. The interesting part here is that I'm giving it the debugger hook configuration, pointing it to an S3 bucket where to store all the tensors. And I'm creating a collection, and the collection defines which tensors to write out. And there's a predefined collection which just grabs all of them. And we're also making sure to include a specific one based on the regex multi-head attention outputs. And this is basically looking for those attention head outputs and also stores them. All right, and with that in place, we can run the estimator fit. So I'm training my model. And I can check here where the tensors are stored. So the tensors are stored in an S3 bucket. And I'm pulling here my training job name. And I'm checking for the training job to finish. And once it's finished here, I can actually create a trial. And a trial is a single environment that points to those tensors specifically. And then I can run commands with a trial. All right, so we do have the tensor stored. I executed the notebook before, so the training is already finished. And as a next step, I'm pulling in now scripts that actually implement the visualization. So also, if you're interested in that, they're part of this GitHub code. So you can see here that, for example, to visualize the attention head view, we're basically using a bokeh script. So this is using bokeh to visualize, and this is the code how to actually plot it. So this is what we're importing here. We're making sure that bokeh also started. And then we can here check for the tensors if they're available. So here, plotted all steps, sounds good. And we're using the trial now to pull information. And here you can see I'm asking for the tensor names. And we can see the 12 attention head outputs here. Then, as the next steps, we're loading in and reading all of the tensors from the 3 epics I was running. We have the 12 attention heads. And then I'm also querying or getting the query and key output tensor names. And here you can see the layers. We're also added some code into the training script to actually capture the input tokens, if we're interested in that for the visualization, obviously. And with that, we can create our first visualization. So let's do the attention head. And here you can see I'm calling the imported utility code that I had for visualizing the attention head based on Tokay. I'm passing in the input tokens, the tensors that I collected, the trial steps, the layers, and here we go. So we do have the first visualization here of the attention head. And this one, if I scroll down here, is visualizing the first layer and the first head. And you can see here in the drop downs that I could also select another head and which step, which is basically my epics of the training. And this will update here my visualization. So in this case, we see with the darker the lines, the more attention is paid to. So a lot of attention is paid here to the question mark, as you can see, in the first layer at least. All right, so let's do another visualization. And what we can also do is this neuron view. And again, as a quick recap, the neuron view is basically visualizing the query and key vectors on a much more granular level now. So you can see even more how the attention weights got calculated. So again, we're querying here for the queries, and here you can see a quick preview of those vectors. And we're also querying for the key vectors, and also can have a quick sneak peek here into how they look. And then we're doing the visualization. So here we're using the other helper utility, which constructs the neuron view. And again, this is here a Python file, which you can have a look at. Again, plotting with bokeh and reading in all of the information needed. So feel free to dive deeper on that one. And we're passing the input tokens, the keys, the queries, which we selected out of those captured tensors, the layers, the steps, and the layer names. And here we go. So here we do have this neuron view. And again, if I select one example here, one query, and this is actually the semicolon here, I think. So it shows you how it attends to all of the other key vectors, which is all of the other tokens here. And the darker the color, the more it attends to, right? So you see here that it attends a lot to those specific tokens. And this is really a good view to visualize how BERT attention works. All right, so this notebook showed you how you can actually use SageMaker Debugger to have a hook into the model training and then write out the tensors. And with a couple of scripts here, Python scripts, you are able to then visualize those 3 different views. Let's jump back into the slides to wrap up the session. I initially said that there's a discussion about whether attention is actually explanation. And another interesting project is actually NLP Interpret. And this one is using gradient-based saliency maps and adversarial attacks to try to explain predictions of NLP models. And I just ran a sample query here with, I love this movie so much, and using Roberta to do sentiment analysis. And what you can see here, it's using 3 different gradient visualizations to actually point to the specific input tokens which cause the prediction here of being sentiment positive. So this is giving a more concrete explanation, whereas the visualization is really just opening up a little bit the covers, and you have to look and find root causes maybe yourself. All right, and that's pretty much the session. Here's a couple of more resources for you if you're interested in learning more. A very interesting blog post on how to detect and analyze incorrect model predictions using SageMaker Debugger. Also the link to this demo notebook if you want to rerun that in your own environment. Workshop with a lot of more NLP use cases, and also how to get started if you're interested in AI and ML on AWS. And with that, thank you very much for your attention.